My name is Edward Chrzanowski. I come from the University of Waterloo. I've been institutionalized up there. Yeah, I haven't worked out in the real world for longer than a couple of months at a time. I started my bachelor's degree there, and while I was taking my bachelor's degree, they said, well, we got this job. You could do it if you want. I said, I had nothing better to do, so I stuck around, and they still haven't released me. So I'm going to talk about Swift in HPC. So the reason why I chose this particular presentation is because this is a MacAdmins conference, and Swift just came out, and it's open source. So what have some of the major clusters been built on? They've been built on Linux, open source, Ubuntu, using Ubuntu or CentOS or Red Hat or whatever you have it. And they were built on open source. Educational institutions use open source because trying to pay for per seat license is a killer. So this has improved quite dramatically from 2.1 that I've been using in terms of the Swift programming language. So these are not the Swifts you're looking for. If you do a Google search on high performance computing and Swift, you'll get the first one. And it's a fast tool for high performance computing. You might even get swift.com, which is for banks. So if you're trying to Google for Swift, you'll get swift.com, and that's the banking code, which was hacked recently in Indonesia. Or you could get something called swift.html, which is an body program. Or you could even get taylorswift.com. Was developed here in Pennsylvania, but I don't know how effective it is in HPC. High performance, maybe, but not high performance computing. And if I wave my hand over your bodies and you're supposed to repeat after me, these are not the Swifts we're looking for. You may continue. That's a throwback to. So you all know where that came from. Good. So before Swift was released, I believe in 2014, it had been many years in the making. You've seen preliminary examples of this in terms of how they were developing the code for the object-oriented programming language they were using, the code. And you could see the development stages in that. The nice thing about Swift that I found very useful is the automatic reference counting. Oh, anybody here remember malloc in C? Yeah, or still work with malloc in C? And the garbage collection you had to do in C? Well, that was some of my research at the university, garbage collection, and I kept telling people I was a garbage collector. Yeah. So I don't have to do that anymore because I could run Swift, and it takes care of the garbage collection for me. And it's familiar to anybody who has used Objective-C. Anybody here run Objective-C and Xcode? Yeah, standard feel. But also the nice thing about this, it's friendly to new programmers. They've even got an educational site. I went to it and I'm saying, this will give Alice a run for her money. Anybody here familiar with Alice? I'm throwing out not keywords here, but Alice is created by CMU to teach children to program. So, heck, what am I doing here? I'm giving a talk. What's the point about all this? You're here in the audience trying to listen to me. So I'm going to give you a tiny bit of rundown on what HPC is, because from preliminary questions I asked, how many people here are familiar with high performance computing and what it is and where it's used. And I'll start talking about some of the Apple Swift programming language and why we should actually consider it for HPC. It's not ready for prime time yet in HPC. Get it? There was a joke there, prime time. This is prime number generator. Yeah. God, you need more caffeine here. So, yeah, sorry, the jokes are flying too swiftly for you, right? Yeah. You'll be here all day listening to me. No. So, and then I'll try and give you a bit of a bibliography in the end. I've got an extensive book collection from my, that's one of my pet projects, is collecting books on high performance computing. And if I haven't got it here online, but if anybody sends me a message later, I'll send you the complete list of books that are very useful for high performance computing. And then hopefully we'll have some questions and possibly swift answers. God, Apple's going to kill me for using the copyright on Swift, right? Yeah, just like the happy birthday song used to be. So at this point, can we actually write programs in Apple Swift on Linux clusters as we can in Fortran, C, C++, Java? Can it be that simple? Well, yeah, we could write Apple Swift programs because it's open source, and yes, I compiled it on Ubuntu and it works, and I could write programs in there. We know we could use GCC on Apple machines. I don't know, has GCD, no. Yeah, that's part of Foundations. That's one of the problems. Now, on the other hand, I could do some high performance computing and port it to my Mac cluster, Mac Mini cluster. So the question asked for this talk is, can we write programs that are intrinsically parallel? Yes, but it's a bit awkward. And this is why I'm trying to give you the talk today on how to get over this awkwardness. High performance computing, and you know, the whole thing about high performance computing is how to crack the passwords faster, or how to get NES, the 28-bit encryption, done instead of in 10 months, in 10 minutes. You know, that's the whole thing about this whole thing, right? Is how to get it done faster. Or in animation, in case of the animation studios, how do we throw out an animated movie that took us 5 years to make in 5 months? That would be great for them. So that's all, the whole basis behind high performance computing. Weather forecasting. How can we forecast? It's great. There's a high performance computing system outside of Tokyo or inside Tokyo, Japan. And that's all they do is weather forecasting. And it's written, the language they use is Fortran. And what they do is that they said, 5 years ago, we could take a swath of ocean that was 100 kilometers, 60 miles for people in America, in square, and now reduce it to about 10 miles. So, and still do the calculation on that, and to a certain depth. So that's how far we've advanced with high performance computing. Same thing in China. Right now, the list of the top 50 computers in the world, few of them are in China. Number 1 is in China. So the US is second, but the US has the most, largest amount of high performance computing clusters or machines together. So that was good. How many people here caught the Go competition between a cluster of IBM machines and the world's Go champion? They said this would never be cracked. Well, it uses a bit of AI in there, AI in terms of searching and trying to guess and so on. But it was run on a cluster as well of many processors. So Go has been cracked, and they said that was one of the hardest things to do. Again, we're talking about high performance computing to be able to create the speed. And what we're trying to do, in this talk is to make sure that we could use Swift in this particular language. So we could do, oh yeah, we're better than HPC, we're Swift HPC, right? Pump your fists in the air, get some exercise going. So this is what high performance is about. Network latency. I'll give you a quick comment here. Everybody here seen the history of the Cray computers? And you open up the Cray computers, you see these large wires hanging from the back from one point to another. Well, they estimated the speed of the electron from one end to the other was 1 meter of wire. So if they wanted a timing done between two transistors, they would actually have, let's say, a 30-meter length of wire wrapped around the back, so that'll give them a 30-second delay. We don't have to worry about that now unless some of us use copper wire cables that are that long between rooms. So we're interested now in terms of getting high performance computing past the teraflop stage into the exaflop and petaflop. So I'm going to give you a brief history on some of the HPC in terms of architecture, models, MPI, OpenMP. I'm hoping anybody heard of MPI and OpenMP? Okay, I've got, sorry for the camera, but I've got references. This is one of the better references on the library. You could get this, you should be able to get this online, but it's called Parallel Computing in C with MPI and OpenMP. I know it's C, but then we could extrapolate to C++ and Fortran and Swift. So there is a crisis in HPC at the moment. If you notice, there's one key phrase down there, the use of order 100K cores or more. How the heck do we write programs that manage 100K cores without any bubble weights? Anybody heard of bubble states in a processor? Okay, yeah, one person over there. Ooh, works for Intel?
No, I work for Intel.
Oh, okay. So you have a processor, and you keep feeding it instructions. And if the processor doesn't keep getting instructions or sends information out, it's in a wait state. And how do you make those processors? It would be nice if we could have all the processors running at greater than 75% efficiency, but that's not the case, even with the current languages and that. Maybe if you get into some inlining and if you write some code that actually works with the processor itself. I've done that. So you have a specific processor in mind and you know the code instructions for those processors, and you could write that in low-level language in your program itself to make use of that. Some people have done that, but to do that takes you months, and whether or not that's another thing. You have to pay these people to code. How do you pay a person to code for 9 months and the application's outdated by the time the hardware comes along? So we have to find different means of programming. So complexity is rising. We're going into the petaflop range. Anyone here care to give me a definition for petaflop? Floating point operations per second. Yeah, so, and then we have to support hundreds of threads in one node. Implies new parallelization. No, parallelization, not parallelization strategies. There's another pun. So programming is stuck. If you take a look at most of the programs in high performance computing, database or in weather reporting or anything like that, you're looking at really good, solid programming languages, Fortran, C. This is just like the brick house, you know, the brick, yeah, outhouse. Good, thank you. So, and then they say software is one of the major components of technologies now. The tradition of HPC procurement to assume that the software was free. Oh, sure, let's run it in Swift. Let's run these programs in Fortran. We got this, we had to pay millions of dollars for this hardware, but we got all these people on the side that were already paying. They could do it for free, right? They don't understand, there are cases where they just don't understand how high performance computing works. So I was thinking, okay, fine. I've worked with C, I worked with C++, I worked with Fortran. How can I actually make Swift work in the same area? And there is, like I said, we're getting into that. So the architectures you're looking at here, you see a name, BlueGeneL, commodity clusters, Beowulf class. Anybody put together a Beowulf cluster running Oscar or what's the other one? Yeah, Rocks, yeah. I use Rocks, sorry. And I've used Oscar. Those are useful tools. It's just management. It just makes management of your cluster easier. Yeah, it's still around.
I couldn't find any, well, anyway,
Yeah, it is still around. You could actually find it, but I don't know if there's any development on that.
that's the problem.
Yeah, but I know Rocks is continuously being managed. But then again, you don't need the management programs. You could always build your own clusters out of telephones. Anyone done that yet? So you take a few telephones together. You could actually run a low version of Linux kernel on telephones, on the mobile phones, plug them all together. All you need, you could take them apart. All you need is the boards, stick them into a container, run some power cords out the back, and you've data cords, you got your programming cluster. Xbox was really nice for doing this, or PlayStation. Oh, anybody put Linux on a PlayStation? Yeah. So, yes. Okay. So, again, the Chinese systems, the Tianhen 1A system, we're talking, these are major air conditioning problems, major clusters. Programming models. The two models that I mentioned at the very top, message passing and shared memory. Anyone here know the difference between message passing and shared memory? Okay, one person does in the back. That's good. You came to the right spot. So message passing, think of a whole bunch of different clustered machines, and you're trying to communicate with them and get the information back to a head node. Or shared memory, you've got a whole bunch of processors, and they're all eating at this whole bunch of memory. SGI, is it still called SGI, or are they called rack something? SGI in the 80s was quite famous for making really good shared memory machines. Expensive, because you're using the same memory, so it's very good. So OpenMP uses pragmas inside the program. I think I've got slides later that do that. So partition global address spaces, languages, next generation programming languages. Anybody here of Chapel, X10, Fortress? I've used Fortress. Is that rain? Ooh. Haven't heard that for a while. So Fortress is an extension of Fortran, or based on Fortran. And it was a language, but it's not being used. These languages that you see here, Chapel, X10, Fortress, they're specific languages for high-performance computing. By the time people are brought up to speed in programming in those languages, they're not really useful. I've got a book that lists over 300 different high-performance computing languages. None of them are being used that often. People are using CUDA or CUDA, if you're Canadian or American. OpenCL, I've used CUDA. Hybrid, I think if I go back one, Roadrunner. Anybody remember what Roadrunner? Not from the cartoons, but the computer. Anybody heard of Roadrunner? Roadrunner was the first installation that was just built on GPUs. And it ran stinking fast. Oh, it could do the n-body program. I don't know what they actually used it for, but I think it actually, one of the calculations was the n-body problem or simulations, Monte Carlo simulations, and they're talking, it was really fast. So that's where GPUs come in, hybrids. And what I mentioned earlier, hybrids, MPI, OpenMP plus CUDA. Well, you can actually run those three in a programming language. I want to do the same thing for Swift. So I asked Maple, Matlab. Anybody here heard of those two? Yeah, you probably use Maple and Matlab. And the nice thing about both Maple and Matlab is that you could go into there, and especially the parallelized version of Matlab, you could say, fine, I want what I've written in Matlab and solved, I want that converted to a Fortran or C program, and it will give you the Fortran or C. I asked if they were thinking about using Swift, and they said, they could not comment on the future product. You'll have to ask sales, as they are the only people authorized to talk about such things. So nothing out of that market. But it shouldn't be that difficult. You just have to convert as an M code for Matlab and Maple into whatever you need for the numerical section for Fortran, for Swift. So I'm not holding my breath for that, so I guess I'll have to write. So Swift is parallel, and it's similar to what C and C++ are without special tools. That's what it is now. So if anybody has written anything in C and C++, they'll know how difficult it is to use the tools that you have available for those languages. So the two things that you could use in Swift are pthreads and dispatch, and I'll give you a brief glimpse of those later in the talk. So currently there is no OpenMP or MPI bindings for Swift. And from OpenMP, they actually mentioned that, yes, OpenMP you could use on ARM architecture. Why is that important to Swift? Mobile devices. You could use mobile devices because they have the ARM processor. So if they have the ARM processor, you could actually write parallel code for them. And like I said, I did that. So there's 32 and 64-bit x86 processors. And you could go to the link I have there underneath to OpenMP LLVM to see where OpenMP can actually be used on different systems. And the nice thing about OpenMP is that you could use it with GCC, ICC, or Clang. If you could use it with Clang, you could then get to use it with Swift. So we're getting close to the roundabout method on how you would use Swift in HPC. So I'll show you a quick glimpse. This is a simple call for parallel programming using OpenMP. If you notice, there's a line in there called pragma OMP parallel 4. That's just a very simple call to OpenMP. The nice thing about using OpenMP is that you could put in all these pragmas, and if you don't have OpenMP on your system, your code will still run. If you have OpenMP libraries and if you link them in, it will use these pragmas. So that's the nice thing about it. You have to be careful. As you do in all programs, make sure your threads are safe. You don't want to come unraveled. So as a statement, as I put below, not yet, but you can do this. Wrappers. Anybody here wrote any wrappers in Swift to wrap code? Wrappers are basically used as that you do all the heavy lifting outside of Swift, bring in the results, and you could use that. That's the same thing as doing a hybrid program where you've got Fortran and C++. Fortran does the heavy numerical analysis and numerical work, and you've got C++ doing the I/O for the disks, because C++ handles that a lot better than the Fortran I/O. Believe me, anybody here written any Fortran I/O knows what I'm talking about. So in Xcode, it's easy. You could also do this on command line. Oh, by the way, before I forget, you could stop me anytime and ask questions, okay? So I just, in this selection here of slides, you can follow this later when the slides are online to actually try this out, and it does work. So I'll still submit the slides at the end of today, and hopefully you'll be able to get them. Again, it's simple. Swift. In Xcode, you go to File, New Project. There's a dialog box. You just click Next, choose a name for the project. Everybody's been doing that in Xcode. Make sure Swift is in the language field. Click Next. So I could do the demonstrations, but if I do, it's taking time away from the talk. In the dialog that appears, you create it. So you've got something created called import foundation and print line hello world. Really simple. And you don't even need one of those lines, import foundation, because you're not going to use any of the foundation features in this particular aspect. You could run it and you get to see hello world printed out in the output pane. Really simple. And after that, you have to create a simple static library using GCC. So this, I've chosen GCC here, but you don't have to use GCC. You could use G++ or C++, G++. You could even use Clang++. So you could use these languages outside. What you're doing is a basic wrapper for the code that you're going to use externally. So what you want to do is actually have this small section in Swift and do the heavy lifting in the code afterwards. This, by the way, will be talked about later when I go into asynchronous and synchronous. Ooh. Anybody, before I get to that, I'm going to leave you a teaser. Deadlock. It's not a movie, it's not a heavy metal CD. Anybody here know what Deadlock is? See, that guy in the back, he's a spoiler. No, yeah. Yeah, I know, you know all about this stuff, but you'll learn, well, you'll hear what a deadlock is in a few minutes. So here we're just creating a simple class, and we're getting an integer, getting private. So it's everybody's seen this really simple small piece of code. So class A, public, and then you create the library's implementation file. So fine, we put in something called junk.h, header files for that, and your standard content. You compile it for C++, and you link it, and the two bottom lines, you'll see G++-C junk.cpp and AR-R, and you create a junk.o. So fine, everything's standard. This is what you do for C++, Clang, Fortran. They're called, in case it'd be Fortran, it'd be F77.0 or junk.f77 or junk.c or whatever. You've got your code, you compile it, and you create the library. So you have to add C++ wrapper to the Xcode project. That's not too bad either, because the C++ code, as I mentioned inside the main title, is called the glue. This is what holds your external code and puts it into Swift. It's written in such a way from C code, and things that can be called from C can typically be also called from Swift. So you add this will be a static library. So what that means is that nothing goes in, nothing goes. It's a static library. So all the stuff goes in, it does the work, comes back with the result. There's nothing changing inside that small section of Swift code that Swift has to worry about. It just knows that it has to pass the information off through the wrapper to your external program and bring it back in. So the library header file, you have to move that into add files to, we're calling this CLI, command line interface Swift, and you add that. Then you go to the file and select C++ file in the dialog that appears and click next. Then you have to type wrapper.cpp in the name field. You don't have to call it wrapper. It can be called other things, but you have to name those variables later. Also create a header file, click next. At this point, Xcode suggests that you create a bridging header. You have to click yes. Otherwise, you create a bridging header manually by going into the Swift compiler and do a standard Objective-C bridging header. So here is the wrapper.cpp tab for the following content. So it includes junk.h, what we put in earlier into the file. External C will cause the C++ compiler to compile the function in such a way it can be called from C and Swift. So this whole section down here, external C, int, get int from CPP, and then you create the instance, and this is what I send into the external file. So if you remember previously, I actually did create a small file, and all I did was get int and wrote a line. So you use Swift C++ from Swift code now via the wrapper. Any C functions you want to call must be declared in the bridging header. So the bridging header, as I mentioned up there, is int, get int from CPP, print line. So this is just the Swift code afterwards. Run the project, and the project comes out with hello world. The value of pi without a decimal is 314159. And that was the value I put into the program previously. put it in here someplace. Right here. Return A314159. So that's the wrapper. Now, another way you could actually do parallel computing is with concurrency. Anybody here know what concurrency is? Anybody? See, there's this one guy in the back. You know, you could come on and do this talk if you want. No, okay. So by default, when you make an application, it runs the code in a single-threaded environment. Swift. If I say, okay, write me give me a demonstration of a thread, everybody should say main. Main is one thread. You send it, you run your program, it gets sent to a processor. That's a thread. What becomes difficult later on is to say, fine, I've got one thread here, but I want to branch off and do other things. And you have to have those processors come back. And that's where synchronization and asynchronization come in. Which method do you think would be better to use in a program? Well, yeah, I know it depends. I like asynchronization. I'll show you in a minute. To a degree. For testing the codes in Swift 3.0, you have playgrounds. So playgrounds, remember Emacs? Everybody here ran with Emacs? You could type your code and actually run the code inside Emacs and see what happens. Well, Playgrounds is basically similar to that. You could actually run your code in Playgrounds and actually see what happens. And type in more code and run it again. And it's a programming environment. It's nice. So you can import the Playgrounds in terms of set execution. And then for what we're talking on the second slide and the previous slide was concurrency. The way you handle concurrency in any programming language is by threads. Now, a word of warning, you could write threads in Swift. I would not recommend it unless you know exactly what you're doing with threads and semaphores. Anybody here know what a semaphore is? Yeah, this is semaphore, the old definition was when the ships went by, they put up flags, and those flags actually was a message, so you read the message, and that was called the semaphore. So all concurrency is built on top of threads and runs multiple threads. So what we're trying to do now in Swift is say, fine, I know I have more than one processor out there, and I want to calculate pi. Everybody here probably seen pi, formulas for pi, like, oh, I forget. I've got pi written down here as well. So what you do is that you take one instance is you'd have a Monte Carlo simulation, runs few million Monte Carlo simulations, and anything inside the circle and outside the circle. You get the area of the circle, circumference of the circle or area, divide that by 4 and you get pi. Or you could take a formula that continues on. So I continue on here because time. You could create threads 2 different ways. One is new thread selector, or you create an instance of NST thread and use that. NST thread is an Objective-C class that uses dynamic dispatch for method calling, which is useful. Instead of solving our initial task, we want to run concurrently. So, as I said in the statement, you must have heard me say, okay, this guy says we're supposed to use threads for concurrency. And now I've got a statement in there, don't use threads. Why? You know, what do we do? Well, because of Apple, you have something called the Grand Central Dispatch, not greatest common denominator, what I kept looking for. You look for GCD on Google search, and it will come back with greatest common denominator. You know, that's a math term. So it's a high-level API that is built on top of threads. You want to use that. It is very useful. And it performs all aspects of thread management for you. So that's some of the heavy lifting that you don't have to do. And it sets up queues, it sets up concurrent queues, it does serial queues, it puts in tasks. So tasks can be blocks of code. Serial, everybody knows what a serial code is. This is where you have deadlock, serial killing. Yeah. Nobody got that pun? Sorry, you're falling asleep on me on this talk. So the main queue, again, you don't have to, you could consider the main queue as a single thread. So we have here particular queues, two dispatches. You have synchronous and asynchronous, and they both look the same. You're just talking about an extra character. So make sure that when you type, you know what you're using. So you've got dispatch underscore sync and dispatch underscore async. And that's the commands that you would see. So dispatch sync, queue, and so on. This is in standard Swift since 2 point whatever. Synchronous dispatch submits a task for execution and waits until this task is done. What I don't like too much about synchronization is the same way that I try to avoid that in regular high-performance computing. Why would I try to avoid that? I've got all these threads running, and they're all synchronous. Pardon? No. No, well, almost. Exactly. So synchronous, you're waiting for these jobs to complete. So you've got 1,000 synchronous threads, and your program is saying, okay, I'm waiting for all these threads to complete. I'm waiting for all these threads to complete. And you're waiting. So why would you run that in synchronous mode anyways? Because you could say, fine, I could run the same program 1,000 times on 1,000 different processors. I don't have to have threads to wait. You know, that's assuming you've got a cluster of 1,000 nodes, and you can run it on the same program separately on each one. So you don't have to do it synchronously. But if you want to use 1,000, 2,000 nodes, synchronicity, it's a good thing for some areas. I'll give you an example. I want to calculate pi. So I have a curve from 1 to 0, you know, standard sine curve. And you calculate the area underneath the sine curve. You assign processor 1. Say you've got 10 processors, so you've got 10 chunks. You have one thread. Calculate the area underneath the square for this one, and then the second processor calculates the area underneath the second square, and so on and so on. So you could have 1 million different squares, and that adds up, and then you send the result and get back pi. That's very good for asynchronous. Why? Because you don't care when the additions come in. Because you're always assigning, if let's say processor 2 takes its time, well, you don't assign the next one to processor 2, the next addition to processor 2, thread. That thread will be there, and it will say, okay, I'm waiting on processor 2, But if processor 2 is the slowest one of the bunch, it will say, fine, asynchronous, I don't care. If it was synchronous, it will have to wait until everything is done. So we've got the queues here. And again, that's what I mentioned in here. Method waits until the task you submitted is finished. Never call dispatch sync function from a task that is executing in the same queue. This would cause a deadlock for the serial queue and should be avoided for concurrent queues as well. So deadlock. Process A or thread A says, okay, I have to use the value in B. Process B says, okay, I have to use the value in A. What's even nice, and it's really great to analyze this code, is if you have race conditions. Anybody know what a race condition is? That's when you have one variable name. It's not static. What you have is that you're writing to that variable name. Process A says, I'm finished. I could write to this variable, and oh, good, I've got this result from process A, so I could use it right away. But process B also writes to the variable name. And you say, okay, good, I got this result, I could use it. But which result are you using? One from process B or one from process A? That's a race condition. If processor B is faster, then you might just be getting B, and you don't know what the end result is because it doesn't cause an error in your parallel program. It just gives you a different result. So on Monday, it could be this result. On Tuesday, it could be this other result. And deadlocks are the same. So you have to be careful when you're using threads. Even with GCD, I find out that once you use the pragmas like in OpenMP and MPI programming, you're looking, why on earth did I ever write this program with threads? So we know that we could use parallel computing with Swift at the moment. It's not efficient. Well, in my case, it's not efficient. It's just not there yet. Give it another year. I wouldn't be surprised within a year we see ports from OpenMP. So GCD has also some other powerful tools. And if you like, you could always go to developer.apple.com/library and look under Concurrency Programming Guide. That will help you a lot if you want to continue doing more work with high-performance computing and Swift. Another thing that you have to worry about is the whole reason behind we're trying to do high-performance computing is that we need to measure how fast we're going. If we're trying to do the program and it's taking us 24 hours, we need to find out where the bottleneck is. How would we find out bottlenecks in Xcode? Come on, some people here wrote Swift code, some people wrote here, used Xcode, right?
Instruments.
Right. And why would you use instruments? Exactly. And that was one of the major things from high-performance computing that's reasonable in this particular case. We could profile. There's a freeware profiler for high-performance computing out in the real world. Take a look online for PAPI, P-A-P-I. That's a nice freeware profiler. It's used extensively, and I've also used that. What you're looking for is trying to get the timings correct. You could see in some of the programs you write, has anybody here used instruments or know what it is? And everybody here should know what instruments is. if you write any code or in Xcode or using Swift. It's absolutely necessary. Because what it actually shows you could do block statements, or you could use break statements, break points in your code, and do timings. What the profiler actually does is shows you, I've spent this length of time in this subroutine. So why is that important in high performance computing? Exactly. So you have in Swift, if you're using Swift, you've got at least 6 different ways of using your NS data. Sorry, using your timing. You could use NS date, CFA absolute time, NS processing information. I could read them, clock in POSIX standard, times in POSIX standard. So you could all use this in your Swift code. Or, as we heard from this gentleman in the front row, you could use instruments to do the heavy lifting. Again, this is a simple program in Swift. Shows you how to set the date and print the seconds. You want to use this instead of wall clock, because wall clock tells you the length of time the program took. It doesn't really tell you the length of time the execution took. It could be the same, but not always, because you could have loading on the processor, and the wall clock might be exaggerated. So performance, how do we know we are doing well? You could use timing functions. You could use some metrics. These are classic metrics in high performance computing. Amdahl's law, Guston-Barsis law, Karp-Flatt metric, ISO efficiency relation. You don't know all this stuff, because if you haven't done any high performance computing, you haven't actually used this to calculate some. Anybody here heard of any of these? One name I'll bring up and I'll mention later. Again, it's Gustafson. Remember that name. And then here, again, Scotty, we need more power. That's Jim Kirk, Star Trek Enterprise, 50th anniversary. He's a Canadian born in Montreal, did some actual acting in Stratford. You know, Stratford, Ontario, Shakespeare acting. So he was actually a Stratford actor, or Shakespearean actor. So I'm just giving a shout out to a fellow Canadian here. And then what happens when Scotty replies, I'm giving you all she's got? Well, you could throw more processors at that point, but it doesn't solve the underlying performance issue. For that, you need to identify the problems, the slow piece of code, and improve it. Key metrics that impact on the performance are operation speed, memory usage, and tertiary usage. Operation speed, performance speed, that's how fast your system is, how fast your processor is. Memory usage. I remember a slide previously I had dealing with the different computer architectures. Well, you have OpenMP using you have many processors using the same memory, and you have the distributed system. Clusters are distributed systems. Tertiary usage. Anybody wouldn't here know what I mean by a tertiary usage? Yeah, exactly. Fine. You've got, what's your L1 cache, L2 cache? What's L3 cache? Those names sound familiar? L1 cache is right next to the CPU. It's a really small chunk, but it's really, really fast. And that's what handles all your processing. L2 cache is right on the chip, but it's next to your L1 cache. Could be on the chip, could be off. Math coprocessors. L3 cache would be tertiary, it would probably be on disk. So if you have to import data from the disk so that into memory so that your program can run on it, that's going to take time. And your processor is going to be idle. And you're going to go into wait states. And that's going to add more time to your program, and that's where you lose your high performance. So first, don't optimize up front. And secondly, measure first. These are two good examples. So when you write your program, don't bother about optimization. Because if you wanted to, what I usually do is write a program, put it in Xcode, and then use instruments and say, okay, it's sort of fuzzy in this area, it's taking up much of my time. I'll take a look what it's doing in that small section. And that's what I said in this first line. You first don't optimize, and you measure. So write your program, measure where the problems are, and then you would actually find out where you could optimize. Again, we're just trying to change the behavior of the codes. For example, we're to use sets or arrays. You know, why would you use an array over a set? Again, this is a question that you have to ask in any language. It doesn't have to be in Swift. So I'll just briefly go over these performance analysis formulas. Amdahl's law is, if you put in the values for this, I give you how to actually put in the values. The maximum speed up of the program. Guffs-Barsis law, given a parallel program solving a problem of size n using P processors, the maximum speed up achievable by this program is this formula. So you can see it's just the processors plus 1 minus the number of processors divided by the times fraction of the total execution time. So the nice thing, or what I mentioned to you that you should remember about Gustafson, is check out another speed up by Gustafson. I know this is a plug. I don't usually like plugging books, but I'm thinking that, yeah, it'd be nice if we could do this in Swift. The book's called The End of Error, Unum Computing, and he specifies a universal number for error. That's one of the problems in parallel computing. You've got a computer system or any program saying, okay, 3.14 is close enough for pi. Sure, in some circumstances. But if you use that value of 3.14 for program and you have to continually use it for your data and in your program, you're going to end up with the circle being a square, almost. That's an exaggeration there. So something similar to that. Again, the flat metric. These are programs, these are just simple formulas you could use to actually determine, okay, I've got this program, this is happening for speeds. How much the serial fraction? How much do you think a parallel program actually is parallelized? It's only roughly about 25% of the program. Most of it's serial. That's a pretty bad number. But then again, if you've got 100,000 or more processors, it doesn't matter. You could keep throwing it at it, or as Scotty was, add more processors to the mix. And the ISO efficiency relation, I don't want you to remember this or to do it. If you needed to, you could always ask me. You could always check this particular book. It has it written in there and gives explanations for it. But these are just measurements to show the efficiency of your program. Performance, Xcode creates unit test targets. And again, you could read what happens to that. Developer.com, developer tools, testing with Xcode. So this is, how many people have put print lines or print statements in their code to find out what's happening? Sure, you've been taught that since the first day of programming. And print lines or print, you have a value of a function, you have a value going into a function and coming out of the function. You want to know what that value is. You take out the print lines later because they cost you money, cost you efficiency, and makes your programs slower. So redevelop print loop, this is the same thing for anybody here used xcrun? XCrun, sorry. That's for Swift. You could actually put breakpoints in Swift. There's playgrounds. Again, I mentioned playgrounds previously, that they were similar to Emacs. LLDB. Anybody here use debuggers? Come on, if you write a program, you have to use a debugger. That's where instruments comes in because it's a nice profiler, but it actually gives you some information on where your program's misbehaving. LLDB is essential if you're going to run threads and want to find out where deadlocks and race conditions are occurring. And again, Apple has some excellent, I'm not a plug for Apple, by the way. It's just that they've written some very good documentation on this. So in conclusion, you can actually do parallel computing with Swift. You could use threads. You could use wrappers. Threads, asynchronous, synchronous. What else would you do for threads to do the heavy lifting? Come on, I just mentioned this. GCD. Remember greatest common denominator if you can't remember dispatch. There's LLDB and REPL and profiler for instruments. Here's a bibliography. This is what I use besides the books I have in my office in terms for parallel computing. So we've got Safari Books Online. They've got one in there, Swift High Performance. It just came out the end of last year. So it's really useful. And I got some information from there. Luckily, I did not know about that book until 2 months ago, before I started writing my slides. Developer.apple.com, developer Apple Library iOS, developer videos. There's nice one, the last. Developer.apple.com videos play WWDC 2016. They talk about concurrent programming in Swift. So anybody here was at WWDC? No. No, I wish. But the people I work for at the university are really selective where they send people to. And since I was institutionalized, they thought it would be best to keep me close to home. Right. So I wish Apple, again, this is a plug for Apple, I wish Apple would give more talks at WWDC dealing with language issues or dealing with programming, dealing with sysadmin information. That's my plug for them. And here's your Latin. Et factum est fieri cito. Well done is quickly done. So if you remember anything from this talk, go away with this tiny piece of Latin and you can impress your girlfriend or your boyfriend. Okay, we won't go there. And this is attributed to Caesar Augustus. Anybody know him? Yeah. Or if you do, I'm just wondering how old you were. No, I don't know him. So this is in many different languages. And I'd like to thank you for listening to my monologue. And I'm hoping that you've learned something from high performance computing and Swift. So technically, Swift is not there yet for high performance computing. You can work with it, but you'll have to work with it. Whereas you could write the same thing in C++ and C, you could use Clang, you could use LLVM compilers to actually run on your computer, run on your Apple device, and actually do some high performance computing. I'd say wait a year before you see the bindings. Anybody know what bindings are in terms of the language? I showed you one of the pragmas. This was from OpenMP. Well, you've got MPI bindings as well that you put into the computer. So it basically has a call to the library, to the MPI libraries, so that you could actually do some performance, high performance computing. High performance computing is not really the same as parallel programming, but they're basically interchangeable. High performance computing, in this case, in the previous case in the bibliography that I mentioned, that the book, they actually say, well, high performance computing means that your program will run faster if you do these certain things. Parallel computing, it means that you're running it concurrently. Again, they've got some instances, the concurrency, but it's getting there. Hopefully, maybe next year I'll just submit this saying, yes, we are there for high performance computing, and these are further examples of programs. If you like, since this is the end of the talk, I've got examples here that I'll send out to people who send me emails. And this is a collection of programs and bindings in Fortran, C++. And they're dealing with, sorry. That's starting from the top. So they're just dealing with a program, how to calculate pi in Fortran or C++, the make files. So you could actually impress your boss or your bosses saying that I've learned some high performance computing. And this can actually be done. You don't need Swift, but it'd be nice if you could write it in Swift as an exercise to the user. I've written it in Swift. It's really simple because it's only a matter of some numerics. And just put it in a loop. You could run it on one processor. It'll take you time, so it doesn't have to be parallel. So that's it. Any questions? I'd appreciate if people know about pragmas being made in high performance computing. That'd be great. OpenMP, MPI. Again, I'll send anybody who sends me email dealing with high performance computing. I'll give you bibliographies and what you should read and exercises if you want that. I'll even send you a quiz. So any questions? There was scratching there. Okay, anybody remember what my name is in English? Last name. Right, so you learned something. You learned a language.